Logic Design, Chapter 5, Lecture 6. Okay, so in the previous chapter, in Chapter 4, we start to talk about how we can apply the knowledge that we have gained in the first three chapters so that we can design logic circuits. And we call this combinational circuit because what we have got is we have got set of inputs, set of outputs derived from the logic itself. And in this type of combinational elements, we have seen decoders, encoders, adder, multiplexers. We can implement any type of logic. Now, when we start talking about chapter 5, this is actually going to be a modified version of combinational logic. So what kind of modification that we are going to do is, we also introduce a storage element. Now this storage element is getting an input from the combinational logic output, and then this is feeding back into the combinational logic. So we can say that in this chapter, which we are talking about now, we will talk about sequential circuits. And this is a typical block diagram of sequential circuits. What do we have in sequential circuits? We have got a combinational logic, we have got a storage element, and we also have a feedback path. So we can say that the output depends on the current inputs, but also the past activity, which is this feedback, through the circuit, and it affects the state of the storage elements. And we can say that this is a present state, and this is next state. So the next state of storage element also depends on the inputs and the past activity. Now, in total, when we look at the all elements together, we can say that the time sequence of inputs, internal states, and outputs define a sequential circuit. So this is chapter 5 in the book, and this is a typical block diagram. So sequential circuits have memory, which we store a binary state. Output depends on the current inputs, also the past activity, and next state of the storage element also depends on the inputs and the past activity. And the time sequence of inputs, internal state, and outputs define the sequential circuits. So we have got two types of sequential circuits in the literature. One of them is synchronous, another one is asynchronous. Now, what is the difference? With the asynchronous sequential circuits, the behavior depends on the signal change in the continuous time. So there is nothing to synchronize with, and whenever the inputs are coming in, like with the combinational circuits, it performs the operation and it gives you the outputs. And we also have the feedback path. So with the asynchronous one, we have got the combinational logic, we have got the memory and storage element, we have got inputs, we have got the feedback path, and we don't have anything else. Now, when we consider synchronous sequential circuits, we have got the combinational logic, set of inputs, set of outputs, also storage element, and the feedback path. So this is present. This is next. Now the difference over here is this is async, let's say, and this is sync. With the synchronous circuits, the behavior depends on the signal chains at discrete instance of time. What do we mean by that? We are actually synchronizing the inputs so that we have got an output based on the clock or train of pulses that fits into the storage element. So that's the difference between asynchronous and synchronous circuits, where in this chapter we will focus on the synchronous ones. But in order to understand the synchronous sequential circuits, we have to understand how synchronous circuits are built, and which is the fundamental building block in there is a asynchronous memory element. So we can say that the difference is over here as well as a formal description. The signal affects the storage elements only at discrete instance with the synchronous one. Other one is hard to design in order for the large circuits. There's a large overhead. And synchronization achieved through the clock from a clock generator. It's much easier to design for asynchronous designs. And most of the industry is using synchronous sequential circuit, and the storage elements change their value in the presence of the clock pulses, as I already mentioned. Now, when we consider a simple storage element, we can say that two inverters, which creates a buffer, is a simple storage element. And you can see that when you connect these back to back, you are actually holding the data there forever. And this is a typical memory element that we use. And one thing that we need to be careful when we are designing this type of circuitries, it requires certain specific procedures and circuit design rules. Now, in this chapter, what we are going to do is we will introduce first the memory elements, which is the fundamental building block in the sequential circuits, because we already know what's going on with the combinational circuits now. We'll need to understand what's going on with the storage elements. And by starting with the asynchronous version and how these are modified through a time so that we can avoid some problems with the asynchronous. And then we'll introduce the clock, which is synchronous memory elements. And then we'll start analyzing and designing synchronous sequential circuits. Okay, so latches is the fundamental building block of all these asynchronous and synchronous designs. They are useful for storing 1 bit of information, and they are generally used for designing asynchronous sequential circuit. And they are not practical, which I will explain in a minute, but let's first understand how latches are working. So in order to understand the latch, I'll start with a simple element of the latch, which is a NOR gate. Now, what do we know about NOR gates? NOR gate symbol, or with an invert in front of it. Let's say we have got A, B, and Y. Now the truth table 0, 0, 0, 1, 1 0 1 1. And it's the inverse of OR. So OR is either one of the inputs are on, output is on. So in NOR, it's either way around. When both inputs are off, output will be on, and the rest will be zeros. So this is a typical NOR gate implementation. Now, in order to implement a latch, we are going to use that NOR gate. It's the basic building block of it, where we will have two NOR gates. One of them giving output Q, other one is giving Q prime. So Q and Q prime, they should not be same. They're just inverse of each other. One of those is feeding back into the second NOR gate, and the second one is feeding back to the first one. And then we have got an input R, which we call it reset, and we have got input S, which we call it set. So this is known as SR latch. So this is the starting point of the memory element. Now, how does this SR latch is working? As you can see, we have got feedbacks, we have got two inputs, and so on. Now we can derive a truth table for SR latch in order to demonstrate the functionality of it. S, R, Q, and Q prime. So I'll start, I'm not going to go in order. I just want to start to show how this is going to operate. So at the first instance, let's say S is 1 and R is 0. That means set will be 1 over here. I'll write it over here. And set is 1, R is 0. Now what will happen? If I consider this NOR gate over here, now if I check the truth table, when if any of the inputs are 1, for example this one, or this one, you can see that output is always 0. Okay, so what I'm going to get over here is always going to be 0 at Q prime. Now this 0 is going to fit in over here, and when reset is 0 and the other input is also 0, then we can see that output is going to be 1. Now I can say that when set is 1, Q is 1, and Q prime is 0. This is known as set state. We are setting the output to be 1. Then let's change the input to both of them to be 0. Now if this is 0 and this is 0, so as we are keeping the previous value in, this 1 that we have got, it will be fed back over here as well. So 1 0 will actually give you 0, because we know that from here. And that 0 is also feeding back in. And 0 0 will also give you 1. So we can see that when both are 0, this is holding the previous value of Q and Q prime. And this is known as hold state. So we have done two possibilities, then we have left two other possibilities. Then let's try the next one, which is going to be 0 1. Now reset is 1, set is 0. So whatever we have done over here, it's now just switching to that one. So when S1, S is 1, we have set that based on this, either of the inputs are 1, output is always 0. Now R is 1 at the beginning. So if any of the inputs are 1, output is 0, that means Q is going to be 0. And this 0 will be fed over here, and no matter, and S is 0, so 0, 0, this is going to be 1. So now we can see that Q is 0, Q bar is 1. And this is known as reset state. We can demonstrate hold again. So when both are 0, now what is happening? This 1 that we have got here, it will be fed back to here. Okay, and when 1 and then the R is 0, so this is actually going to get 0 again. Okay, so this will be 0, and that 0 is going to fit over here, and 0, and this is going to be 1. 0, 0 is going to be 1. So we are holding the previous value. Whatever you have got over there, it's copied down. Okay, this is what hold is doing. And the last state, when both inputs are 1. Now, when both inputs are 1, that means output is going to be 0 on both of these NOR gates, either here or here. Now, at the beginning, I said that this is Q and this is Q bar. So inverse of something is not going to be equal to that thing. So this is not possible. And we can say that this is invalid state. So invalid state is causing a problem in latches because you can get into that invalid state and it will hold there forever. Okay, so from the lecture notes as well, I'll just demonstrate it quickly. When set is 1, we are setting the output to be 1. When we change the input, so we are setting the output to be 1 because if either one of the inputs are 1, output is 0. So as this is 1, this will be 0. That will be fed back, and 0, 0 will give us 1 based on the NOR gate. And then when both are zeros, that means this one will be fed in. So 1, 0, it's also going to give you 0, and this will be fed over here. So 0, 0 will also give you 1. So you are keeping the previous outputs. Then when we change S to 0 and reset to be 1, we are actually forcing the output to be 0. So in this point, at this point, as this is 1, then any of the inputs are 1, output is 0, then this will be 0. This 0 will be fed back. 0, 0 will give you 1 for the Q bar. And you can see that output is going to be resetted to 0, and output bar will be 1. And we try hold again. So when both are 0, as we are having the previous output kept over there, so that will be fed in. 0, 1 will give you 0, and 0, 0 will give you 1, and we have got the same as the previous one. And when both are 1, that means both outputs are going to be 0, which is not possible as one of them is representing Q bar, then it's an invalid state. So we can also extend this table, and we can rewrite it or derive it in a way that we can find out an expression for it. So let's do that. We have got input S, R, Q, present, and Q next. Q next are generally written with Q plus. You can also write Q plus inverse. Okay. Now, let's say these three are our inputs. So the present state, where is that coming? That's coming from here. So that's the present state. Okay, that will be fed in. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, it's the same thing, nothing is changing. We just know the present state as well. We are assuming that we know the present state. So that's present, that's next. Okay, so when S and R is 0 at these 2 points, when both are 0, it's the whole state. So whole state means whatever we have got on Q present, it will be reflected to Q next. So 0, 1, and 1, 0. Because this is the present, SNR is 0, that means holding the previous value. That means whatever we have got on present, it will be reflected to the next. Nothing will change. Then 0, 1. Now reset is 1. No matter what's happening with Q present, as reset is forcing output to be 0, Q plus is going to be 0, Q plus inverse, it's going to be 1. Then 1, 0. Now 1, 0, set is 1, so we are forcing output to be 1 no matter what's happening with the present state. So this is going to be 1, 1, and this is going to be 0. And in the last one, as we already said, when both inputs are 1, it's invalid because both Q and Q plus are going to be the same value. Rather than putting invalid state, what we do generally, we are specifying them as don't cares. Okay? We don't care about the output because it's invalid. So we put X's. Now, in order to derive the next state equation for Q, I have to draw a Carnot map for Q next. And I have to put everything into a Carnot map. So we are going back to chapter 3 again. We have to know the Carnot maps. And 0, 1, 0, 0, 4 is 1, 5 is 1, 6 and 7 is X. Now, if I combine, I can see that this can be combined. By the way, I have to specify that this is S, this is R, this is Q. So I can say that Q next is equals S, or I have one more here, which I can combine those two, R prime so this is R prime Q. That's our next state equation for this SR latch. You have to know this because we are going to use this a lot. Okay, so this is the first next state equation that you will need to remember, and that's the formation of the SR latch where we have got two NOR gates and the output of one is fed back to the other one and the output of the other one will be fed back into the other one. So the same things are derived over here. When we plot onto the K-map, we got S or R prime Q. No matter what way you do this inputs for the K-map, you're still going to get the same output. So we can also demonstrate this with the latch waveform. So timing waveform shown over here. At the beginning, S is 0, reset is 1. That's why output Q is 0, as reset is forcing output to be 0, and output bar will be 1. And when both are 0, we are holding the previous value. When set is 1 and reset is 0, that means Q is going to be set to 1 because we are forcing output to be 1, and Q bar will be 0. And this goes up until here. Then when both are 0, we are holding the previous value over here. Then reset is 1. So when reset is 1, that means we are forcing output to be 0 as S is 0. And this goes up until here. And when both are 0, we are holding the previous output. Then set goes up again. Reset is 0. That means we need to set the output to be 1 over here as well. And then when both are 1, we are going to get 0, 0, which is an invalid output. And after that, when set goes low and reset is high, then Q becomes 0 or stays 0. So we can demonstrate the same functionality of the truth table with also the timing waveform. We can also implement the SR latch using NAND gates. It's like an active low version of the SR latch. So everything is inverted. The operation is inverted. So when both are 0, it's an invalid state when compared with this one. And when it is 0, 1, it's not reset now, it's a set state. Okay, and 1, 0 is a reset state when you're using NAND gates, and 1, 1, it's going to be the hold state. Okay, this is the NAND implementation, the same approach, only the polarities are changing, and we are getting active low outputs. Now, this invalid state will cause a problem, and the designers have tried to avoid this or modify the circuit so that we can get rid of that invalid state. And one of the modifications that they have done was SR latch with control input. Now, what is that control input? We still have the latch, but we also have a control input which is feeding it to the enable. So we add 2 AND gates as a enable logic, okay? And when control input is 1, we are activating reset and set. If the control input is 0, then these inputs are not going to feed into the SR latch, so there won't be any operation. It's actually holding the previous value. Okay, so you can see from the truth table, when C is 0, these are not activated. We are not feeding any data into the SR inputs, and we don't care about those. That means we are holding. Nothing will change. The same applies for the NAND. If you want to implement everything with a NAND, you can use and invert NANDs over here. Then, when control input is 1, that means we are activating the circuitry. When both inputs are 0, it's again using the SR latch basic phenomena. When both inputs are 0, we are holding the previous value, and that means hold, no change. And control input is still 1, so the circuit is active. If reset is 1, it's a reset state. When S is 1, it's a set state. We are setting output to be 1. And when both are 1 and the control input is 1, it's an invalid. We cannot do it. Now, why are we doing this? Why are we introducing this control input? As you can see, when we introduce a control input, Now you can see it from this truth table that instead of having this hold, I can use this as a hold as well. So when control input is 0, then it's a hold. Why am I doing this, or why the designers are doing that? Because they want to modify the circuit in order to make it the way that S and R, because over here when S and R is 1, it's invalid. And we can avoid this S and R when they are equal to 0. So when S and R equal to each other, we avoid those operations. That's why we had to introduce some other hold state. Now, another modification is done, and the designers introduced D-latch. Now, D-latch is the one that is used a lot. Again, it's made up of SR latch, but the modification in the D-latch is that you have got the input, which is feeding into the NAND gate, for example, which you are going to get the S prime, and that will be fed into the NAND gate, and you have got Q. And on the other side, we have got another NAND gate, and the NAND gate for the latch. This is R prime. And we have got the same D feeding in, but we have to be careful because we don't want both inputs to be same at the same time, as we want to avoid the invalid. So what we do is either we are getting 1, 0 or 0, 1, so they're inverse of each other when they are fed in. And the control inputs, control input is activating the latch. That's how we use it. So this is a typical D latch, Q prime, that's feeding back in. This is feeding back in, and that's it. This is a typical D latch. Now with the D latch, as you can see from the operation wise as well, we have got C, we have got D input, and we have got Q plus and Q plus bar. Now, 0, when control input is 0, we don't care about X because it is actually making this as inactive. So no matter what's happening with the D input, it's always hold. So I can say this is hold. Now when control input is 1 and D is 0, then what will happen? As D is 0, it's going to be Q will be 0 and Q plus will be 1. So this is actually reset. And when control input is 1 and D is 1, then it's going to be output as 1 and output prime will be 0, and that will be set. So we still have hold, reset, and set, but as you can see, we don't have invalid anymore. So we don't use invalid state, and we don't use 0, 0 state when both inputs are equal to each other. So we introduce this inverter, we introduce the control, and this is now the new latch, which we call it D-latch. And D-latch is introduced to eliminate undesirable condition of indeterminate state in SR latch, and it ensures that S and R never going to be equal to each other. Two inputs, D and data and control, which will be used. So the operation is shown. Now, if you look at the timing waveform, you will see that when control input is 1 and D is 1, output is 1. When control input is 0, as we don't care about D, we are just holding the previous value. So previous value is 1, so the next value will be 1. Then at the control input is 1 again, that means the circuit is active. We check for D. D is 0. Okay, what will happen when D is 0? Output will be set to 0. So output is set to 0. Then control input is 0, so circuit is inactive. We have got 0 in the previous output, then that will be reflected to the next one as well. And the last one, control input is 1, D is 1, then output will be 1 and 0 and 1. So you can see that output is following input D when control input is 1. Now this is called level triggering. So output can change based on the input data D when C is equals 1. That means the logic level 1 at C input triggers the D latch. That's level triggering. So you can also expand this and find out the equation for the D latch, which is Q next is C prime Q or CD. This is the equation for the D latch. And D latch holds the data when C is 0. Output can be changed based on C. When C is 1, it's level triggering, so output follows input. And since the state of the latch follows the input as long as it stays in the triggering logic level, the latch is level triggered. We already said that in the timing waveform. And the latch is transparent. It means that it's going to reflects the output input to the output. It's transparency over there. And we can easily see that when C is 1. So if I go back to the timing waveform, when C is 1, output follows input. When C is 1, output follows input. When C is 1, output follows input. That's what we are looking at as a transparency. So if you look at this circuit, I don't know if you will notice something, but there's a problem over here. Now, what is that problem is, imagine that this is clock or control input, C. And this C is activating 3 different latches at the same time. Now, think about it. You're sitting and you have got an object on one hand and there your friend is sitting next to you. Now, if I clap my hands and at the clap of my hand, you have to switch the object in your hand, for example, a pencil, from your left hand to the right hand. Now, what will happen when you are switching? At the same time, let's say your friend is sitting next to you, he or she also needs to switch the object from left to right because you are just doing the same thing. And the friend next to you, next to him or her, also doing the same thing. Now, what will happen as the first one, as you are trying to switch the object from your left hand to the right hand, and as your friend is going to look at your right hand to find something and switch it to their right hand, then this will cause a problem. Because as they are switching at the same time, now I feed in an input over here. Now the control input is 1, control input is 1. Now this is transferring it, but as they are activated at the same time, this will not find any input to transfer it over here. This will cause a transparency problem. So they are going to keep update their cells and there will be an unreliable and unpredictable final state. So let's see from the timing waveform, the control input or the clock is activated, low, high, low, high, low. It's like a train of pulse. Now input is 1. It's always 1, as you can see. It's fitted over here. Now Q1 is going to see high, low, high, low, high, low, high, low. Okay, because as this is feeding back in as well. Q2, high, low, high, low, high, low, and Q3 is also like that, but it's inverted. And this is happening when clock is 1 only, because all of them are working with the clock 1. Now, in order to avoid this transparency problem, so they are not going to be activated at the same time, what I can do is I can invert this clock over here. So if this is active, this is inactive, this is active. So this will transfer the data to here first when this is sleeping, And when this is awakened, this is sleeping, so it's not going to change the data over here. This will take the data and switch it to other one. And also this one is sleeping at the same time while D2 is active. Okay, so this can be modified. As you can see, the clock is inverted, or the control input. This is active, inactive, active. And when we do the simulations, you will see that clock going in, input always high. Q1, as you can see, it's more stable now. Q1, we feed in data. Now Q2 is going to be activated when Q1 goes to 0, because this is inverted. This is going to be activated. Now this will be activated until here, okay? And then Q2 is going to see, Q2 is going to change when this one is activated, and Q3 will change when this one is activated, okay? So these are all initial conditions, and then it will change back again, as you can see. Now, this is a how to solve a transparency problem, and most of the storage elements are using this approach because they don't want to cause any problem. They want always to be in a reliable state. That's why we can use this formation.